course, one of the classic unimodal models of the circle is the von Mises distribution. What is the relative efficiency between the two estimators in that particular case?
I assume you mean that one calculates the maximum likelihood estimator, or compare to the extrinsic versus intrinsic?
Extrinsic versus intrinsic.
Extrinsic versus intrinsic. I don't know. I haven't computed that. Maybe I shouldn't guess. But it's an interesting question. I shouldn't guess.
Can anything be said about how these means behave under convolution if you know the mean of two densities and then you convolve those densities? Can you say anything about the mean of the result?
Also a good question, which I must say probably can't answer easily. Well, if you have a unimodal density, obviously it remains unimodal if you convolve. And so you have still uniqueness. And you get closer to the uniform distribution, and so both means will behave reverse. This is because in the extrinsic case, what will happen is that the mean will get closer to 0 in the ambient space. So the regular Euclidean mean gets closer to 0. And then in the central limit theorem, that is basically the denominator in the asymptotic variance, the expectation of Leibniz's absolute value, distance to the origin. And so this deteriorates. And similarly here, the density will become smoother, it will be closer to the uniform distribution, and so also this variance will go down. But which one goes down faster, I cannot say.
My question would be if you, if you change a little bit the geometry of the circle, if you deform a little bit the circle, instead of looking at the circle, you work with something which is just a small deformation of it. It will not change anything for the intrinsic mean, but it will have an impact on the extrinsic. Do you have some idea about can you extend more or less to say if you deform a circle, you get more or less the same property for the extrinsic? Do you have?
Yes, for the extrinsic mean, I think that is well known. So if you look into the paper by Battaglia and Patanjala, it's 2 papers actually, you will find theorems that basically say, well, as long as the projection is unique, then you can apply this methodology if you have a smooth manifold embedded in some ambient space.
So it means, in fact, we have the same result.
They are qualitatively, you have the same results for the extrinsic. Yes. Obviously, if you have a small notch, which is close to where you're projecting, the behavior there will be different. So if you're close to this, but otherwise it will not be different. But qualitatively, you have the same.
Okay,
so it's only quantitatively it will change. It will depend on the curvature, because your projection will depend on the curvature at this area. This is again, the curvature is encoded, if you like, in this expectation of the absolute value of expectation of it's the distance to the origin, but in this case it's also this is the ratio, the circle for which you project.
So you looked at a circle, but what about higher dimensional manifolds?
So again, for the extrinsic mean, it's simple, in a sense. For spheres, I'm trying to work this out, just to work out whether how much mass basically you can have on the opposite side, so that still the mean is unique and that you get central limit 0. But it's more complicated in higher dimensions than on the circle. Here, you have the advantage of being able to make the calculations all explicitly. Whereas on the sphere, it's no longer that simple. But, it's working.